This session is one in which we're talking about building models and for calculus. Inside Semioid, we concentrate on differential equations, but a good number of people at meetings and so forth say, do you have any models that we could use in calculus? And so you're about to see the penultimate model, which is an iconic model, but I'm sure that Tim never tires of talking about it. Tim, I believe, was at Hope College in Holland, Michigan at the time. Is that right?
That's right, yeah.
Yeah, and a number of you probably have seen the publication and know about this Corky, and I'm going to let Tim tell the rest of the story. This is Tim Pennings from Davenport University in the heart of Michigan.
Very good, thanks, Brian. So yeah, Elvis came to live with me back around 2001. And I live just stone's throw, 30, 40-minute bike ride to the nice sandy shore of Lake Michigan. And Elvis went everywhere with me. He'd come to class with me, sit up on the desk. I had a student tell me that he softened my image as a teacher, which I'm sure he did. Sitting up there and receiving the pets of students on the way in and out of class. But anyway, I took him to the beach and I would throw the stick into the water, and might as well kind of get going on this as I do it now. So let's see here. There we go. So I would throw the ball to, say, point B, and Elvis is with me at point A. And so I normally give this talk in 50 to 60 minutes. And an important part of the talk when Elvis was alive was to go into a hallway and have all the students line up on either side. And I would toss a ball down the hallway and Elvis would scurry to get it as quickly as possible. Because one of the things I do in the talk is to really stress that mathematical modeling involves being aware of your assumptions. And one of the assumptions that I was making with Elvis is that he wanted to get to the ball as quickly as possible. And so it made a great excuse for bringing him with me into all these high schools all over the country, let alone universities and colleges. And lining up the students and then seeing him scurry down the hallway as fast as he can to get a ball. And I would normally ask if there was some track star there in the group. And if there was, then they could race Elvis. And it was pretty easy to guess. If the floor was carpeted, Elvis would win. If it was a nice tiled floor, then the student would win, because Elvis's his claws didn't stick very well to the floor. But anyway, so that's what we did. And so then I'd ask the students, I'd say, well, what's the fastest way to the ball for Elvis? And I'd explain, of course, that the shortest distance is just to swim straight there through the water. And then ask, well, why isn't that then the fastest one time-wise? And of course, they would quickly give the answer, well, he runs faster than he swims. So then another extreme would be to go all the way to the corner to see, and then to swim the smallest amount as possible. So those are the two extremes. And then the third option, and I'm doing this in about a third of the normal time, so I'm talking fast, but I'm assuming my audience catch on, obviously. So the other option then is to kind of split the difference and to go to some intermediate point, which we'll call D. And that's what, in fact, he did. And so once I saw that he did that, then it just triggered in my mind, well, this is what I do every year when I teach calculus. For me, I call it a Tarzan Jane problem. One of them is sinking in the quicksand. The other one's got to cross a stagnant river and run along a beach to get to their partner as soon as possible. And it always ended up being a path similar to the one that would go from A to D and then from D to B. So that's what Elvis was doing. And so it just became a question then of discovering how close was he coming to actually going in at the optimal point. So that's what I set out to do. So when I give this talk, depending on when I give it, I give it to PreCalc students sometimes. And then I just explain what it means with calculus, that positive slope is where it's increasing, and negative slopes where it's decreasing, and the max and the min occur with a zero slope. So then this is all stuff you can do nice and slowly with students. And by the way, for any of you who are watching this, I'd be eager to continue going around giving this talk different places. I have video of Elvis. I won't show it now, but I have video of Elvis, which is in lieu of him being there. He died in 2013 after a good ripe age. But anyway, just asking the students, what's the function for the amount of time it takes Elvis to get to the ball, given that he goes in at point Y? So obviously the distance that he runs is Z minus Y, and you divide that by his running speed. And then you take the distance that he swims and divide that by his swimming speed and add those together, and you get the total amount of time it takes him to get to the ball. And then I like to ask students, just by thinking of this physically, what would you expect this function to look like? And so it's just full of nice questions you can ask students. And hopefully they come up with something like this, that if Y is equal to 0, if he goes in right at the corner, that it's going to take a certain amount of time. If he goes in before he gets to the corner, it's going to take less time. But then if Y is too large of a number, then he's spending too much time swimming, and the time is going to increase again. So they start getting a sense of the graph of the thing, and then of course explain to them, and they see that what we're after is finding what's the value of Y, which minimizes it, and that's going to be where the derivative is 0, where the slope is 0. So there you go. So so then the question is, how do you get the slope? So I always go over this carefully with students, and they have trouble with it. Y is your variable. So to break that up and to say that Z over R is a constant, that takes a little bit of thought. I'm going to have to use a chain rule there for part of it, but they can do all that. And we usually go through that together. And by the time we're done, and then we have to set it equal to 0 and solve it for Y. And when you solve it for Y, then you get this kind of nice looking equation, which involves the running speed and the swimming speed and how far you throw it into the water. And there's your value of Y, which gives the minimum time. So so it takes us 15 minutes or so to go through that, and that's all good use of review of calculus and algebra, which is sometimes the sticky point for them. So then here's my favorite question. I ask them this. There's the formula down in the bottom left. And I ask them, now, what would happen if instead of starting at A, if I were to back up another 15 meters down the beach, I still throw it to B, so there's just a longer distance involved. And the question is, what should Elvis's strategy be? What happens to the place he goes in? Instead of going in at D, if D is where he should have gone in if I threw it from A, what happens if I back up now? How does Elvis's entry point change if I were to back up 15 meters? And I give him some options. I say he goes back the same amount, 15 meters. He goes back a proportional distance. He stays where he is, or actually goes forward. And can people can I get responses here? What should Elvis do if I were to back up 15 meters? I don't know if I can hear anyone or not. I'm not hearing anyone. I'll keep talking.
I'll say it. Can you hear me?
Yeah.
I think your head's a D, but I've done this problem. So.
Yeah. Okay. Very good. Yeah. I mean, if you look at the formula, the answer is it doesn't change at all. There's no Z in the formula. Notice, and it's such a beautiful thing to show students, because I just explained to them. I say, you can get an education by going out and getting a job, by living on the streets, by joining the military, by traveling the world. There's all sorts of ways to learn a lot about life, but the way you get a liberal arts education and learn some of the most important, powerful stuff ever discovered by the human mind is in a college setting. And this is one example of it, where if you just let your intuition tell you what you think it should be, everyone, 90% of the students and faculty for that member would say, no, he should back up some proportional distance. And then I say, here's the power of mathematics right here. This shows you the power of mathematics, that it cuts through all that intuition, which may or may not be right, and it gives you the correct answer. So what power? So it's just a wonderful way to key in on that fact. So anyway, so that's the key thing right there. Then here's some other ones. If he swims faster than he runs, then what should he do? And again, just for the sake of time, I'll go through this. If you notice, if he swims faster than he runs, then R over S will be less than 1. So when you subtract 1 from it, you get an imaginary number there, which means there's no critical point, which makes sense. There is no critical point. He should, if there's no critical point, the max and min are at the endpoints, and that's what he should do. He should just jump in right from where he is, because if he swims faster than he runs, he might as well go the shortest distance. So there's that one. If he runs much, much faster than he swims, that's my notation for that, then you think, well, it seems like the logical thing is he'd kind of run as far as he can pretty much and then swim the shortest distance. And notice the mathematics bears that out as well. I think you can see my cursor.
Mhm.
So if R is much, much bigger than S, then this is a big number. That's a big number. You multiply two big numbers and you get a big number. You divide by a big number and you get a small number. So sure enough, Y is small, which means he goes almost to the corner. If he runs almost the same as S, then this is kind of fun. People will first say, well, then he should split the difference, run halfway and swim halfway. But you look at the mathematics and you say, well, wait a second. If R is just slightly bigger than S, then this is close to 1, which means this is close to 0. If you divide by a small number, Y is big. And you think, oh, of course, if he runs and swims at about the same rate, then he might as well, again, basically swim the entire way. So you think, oh, yeah, sure. So there's the mathematics. And it's so nice to do a problem like this where instead of just putting numbers in there, the parameters are in there, and they can learn so much by having the parameters there, and they can understand at a deeper level what's happening. So good for lots of reasons. Finally, if once S and R are fixed, which they are, you never should say fixed to a dog, then notice that Y is just proportional to X. And so I went back to the beach, or I went to the beach, and I took his running speed by having a friend and I throw his Frisbee back and forth half a dozen times. And then his swimming speed, I got in the water and he swam after me as fast as he could. And my partner marked 2 spots on the beach that were 10 meters apart and got his swimming speed, came back, stuck those in, and we found that there's the relationship between X and Y. And so there's red line right there gives what Elvis's choice of Y should be. If I throw the ball 16 meters into the water, his choice of Y should be a little bit more than 2 meters. So then I went back to the beach to see once how close Elvis was coming to this. So at this time I was alone. So here's what I did. I staked a tape measure right to the edge of the beach, right here. I backed up about 20 meters and I practiced throwing the ball so that the ball would fall somewhere along this perpendicular line. Of course, I never got it exact, but I took that into account when I made my measurements. Once I got good at it, I brought Elvis over with me, next to me, and then I threw it. He went, oh, and I had a big old, what happened to my cursor? There it is. I had a big old Phillips screwdriver in my hand. He went scurrying after the ball like this. He went down the beach and then jumped in and swam. I ran after him with a Phillips screwdriver. I plunged this Phillips screwdriver into the beach right where he went in. I had to explain to some folks why I was chasing my dog with a Phillips screwdriver. I was doing a science experiment. Now he's swimming towards this thing. I quick run and grab the free end of the tape measure, and to his shame, I am still able to get out to the ball before he does. And I get there, I give him the ball, he brings it back in with me. I take this measurement, and then I take this measurement, and that's what I needed. So once I had those, by the way, isn't he a handsome guy? There he is coming out of the water with the ball. Once I have those, there they all are. And so I put those into Maple. There's a nice scatter plot of them. And so then the question is, how close are all those to that red line, which was the optimal? And there it is right there, which is really cool. So a typical distance is about this far, which is about that far, about 1/3 of a meter, about a foot. So he went in good bit of time. He went in about within a foot of the optimal point. I won't take time to talk about that today, but this is a nice example of the smooth and the rough. And there's some things to be learned from both the smooth and the rough here. So there's that. Then, as I say, modeling assumptions. So this is fun because even if you do this in a pre-calc class or whatever, if students don't understand for whatever reason the calculus, depending on what they've had, you can always ask them, what are some of the things that we assumed to be true here in order to do this model? And it's a wonderful part of it. One year, and again, I take five or 10 minutes and let them come up with things, but that there's a definite line between the shore and the lake. The waves come up, so you have to decide where is that line. That he starts swimming as soon as he got in the lake. I'd always lift Elvis up and show his legs and show him that he only had about 5-inch legs, so he had no choice but to start swimming pretty quick. But if you had a golden retriever or something, then you'd have to take all that into account. Another one is that the ball is stationary, that once the ball hits the water, that it doesn't move much. Another one is that the values of R and S are constant. And so again, those are all assumptions that you're making. Even if they aren't quite constant, more than likely they maybe would get slower at about the same rate. So, but those are still assumptions. And so that's all good. Then I always have fun by talking about, does Elvis know calculus? And what I would do is I'd put him up in front of the class on a table, and I would get in the back. So by looking at me, everyone could see his face. And then I would say, okay, now you watch his ears and his eyes as I ask Elvis the derivative of x cubed. And so then everyone's watching them, and I say, Elvis, what's the derivative of x cubed? And there's just the silence as everyone's watching them. And I say, there, see his eyes, see his ears, see what he just did with his ears, see his eyes. And everyone's what? And then I explain, he didn't do a thing. I've become convinced he doesn't know the derivative of x cubed, let alone the derivative of this Messier function. And so that's what's so amazing, is that he knows how to do this somehow instinctively rather than doing any of this calculus in his head. So, so anyway, have a lot of fun with that. Optimizing ability of nature. Then this is a great way. Then sometimes I'm in schools where I'm afraid that maybe evolution isn't even allowed to be taught, but without ever using the word, I can just say, hey, how did Elvis get this ability? His ancestors, the ones that were able to maybe see a carcass on the other side of a river, the ones that got there first were the ones that ate, the ones that ate were the ones that lived, the ones that lived were the ones that reproduced. And so just from natural selection, Elvis is the recipient of the ability to make good choices like that. And then I talk about if you take blow into a soap bubble, you get a nice sphere. If you take a bunch of wires and dip it down into a soap solution and lift it up, you're going to get all these interconnecting planes, which is a what do you call it? A calculus of variations problem. Other things like birds will learn to drop shellfish from the right height, so that if they go too high, they wasted their energy. If they go too low, they won't crack. So all these different examples of light going through a prism. Light going through a prism is really just trying to get from point A to point B in the shortest amount of time. And so when it goes through the glass, it alters so that it doesn't spend so much time in the glass. So these are all examples of how nature finds the optimal solution. And Elvis is just one example of it. So, further experiments, you can do dog and snow. You can do children. I make a joke. I say I wanted to do this with fraternity guys, but I'm afraid after throw a bottle of beer in the water and let that be the incentive. But I'm afraid that maybe the results might get bad after a few trials like that. Here's some pictures of Elvis. There he is on the college math journal. He was on Focus. There's the article about him. MAA, they sent around 500,000 of these. They used Elvis to kind of publicize the MAA back in 2004 or 5 or thereabouts. There he is. There we are on the Holland Sentinel, a front page of the Holland Sentinel. My dad visited an elderly man and who had this on his coffee table. And my dad said, yeah, you see my son's picture in the paper? And this man says, yes. He says, I saw the picture. What an intelligent looking dog, he said. So So there you go. I have a student friend who said, what's it like to become famous as a mathematician just because you have a dog who's better looking than you, even when he's running away, was his question. This is someplace, this was in, I can't remember. Some of these have appeared in textbooks. Here's Muse, Current Science. There's Corgi Cryer. How many of you get the Corgi Cryer? What's his name? Oh, shoot, the math guy from NPR. I can't say his name now. What's his name?
I know who you're talking about.
Yeah. He wrote an article. Oh, here it is. Keith Devlin. He devoted the second chapter of a book to Elvis, and he spoke at a joint meetings with 3,000 people there. I had never met him before, so I came up afterwards. There was a whole crowd of 50 people waiting to meet him. When I finally got close to him, I stuck out my hand and said, "Keith, I'm Tim Pennings, and here's all these people around." He goes, "Tim," he says, "I didn't recognize you with your clothes on." And, what? And he goes, "Well, yeah, all these pictures I ever got of you and Elvis for my book, you're at the beach and you're without a shirt." So anyway, he was a biographer of Elvis in this book. Here's one from Switzerland, I believe, a book of crazy experiments. This is from Her Majesty. I sent her two copies. I signed one for her and asked her if she'd be so kind as to sign one for me. And a month back, I get a package from Buckingham Palace, and I tear it open, and there's my journal, and I'm all excited, and I read it, and it says, "The Queen was very interested to read about your dog. However, as you see there, Queen's made it a rule only to give her signature to people personally known to her. I don't have that rule myself, so I didn't mind signing one for Her Majesty. But I kept the journal. Anyway, I figure how many people have been spurned and rejected by the Queen of England. So there's a claim to fame, I guess. And there's Elvis with some of his favorite sticks. Brian, do I have like 2 more minutes?
Oh yeah. I'm the next speaker, and so I'm just going to reiterate some of the stuff you're doing. So you're doing great. And
super. Okay. I'll take a couple more then. This is the end. If I have to stop, there's Elvis's end. There he is. But then these two mathematicians from France, they tried it. They got all this publicity, and they checked it out with their dog, and they got the same result. Their dog did the same thing, but then they got a real interesting idea. They said, maybe our dogs are not doing max-min problems. Maybe instead they're doing related rate problems. And so they thought of the problem like this. They said, perhaps what Elvis is doing is he's running down the beach, and at every point as he runs down the beach, he asks himself the question, what should I be doing at this particular point in time and place in order just to be moving towards the ball as quickly as possible? So there's no kind of global decision about what global path will get me there minimum time. It's just that at every point in time, you're trying to move towards the ball as quickly as possible. And if you think of it that way, you can see how it might be a similar answer. If he's right here, he has a choice of either swimming slowly like this or running more quickly here. But as you get closer to the ball and the angle changes, at some point, it's going to be advantageous to be swimming slowly like this rather than running quickly like that. And so if you do the problem that way, here's your distance right here. You take the derivative of the distance, then you assume that x prime is 0 because it's not moving in the water. And z prime is just your running speed. So that's just r right there. And then you ask, where will that, this is the rate at which his distance is changing. When will that rate be equal to s? Because as soon as he jumps into the water, then he's swimming straight there with a speed of s. So you want to know, when will this speed as he goes along the beach, when will that be equal to the speed when he jumps into the water? So you set those two equal to each other and look at what you get. Same thing as before. So this is a deep problem. What problems are there? What is the class of problems where thinking of it as a related rate will give you the same answer as thinking about it as a optimization problem. And so this is another paper that I did with a couple other mathematicians. I forgot what the name of it is now. Elvis Lives. It started out by saying Elvis Lives. It was in the College Math Journal. And we basically looked at this whole question of when are these two the same. But anyway, this became an interesting question. So then the question is, which one of these is Elvis doing? Is he making this this global decision, or is he doing this, moment by moment, a local decision? And they sent CMJ sent me the journal to review, and I reviewed it and said, yeah, look, great article. Go ahead and publish it. A couple weeks after sending in that review, I happened to be back at the shore with Elvis. It was a hot day. Elvis was in the water with me. I tossed the ball a little bit away. He swam to get it, and he brought it back. Then I tossed the ball a long distance away. And as soon as I did, I realized, aha, this is significant. If Elvis is doing what they suggested, he's going to be moving towards the ball at every point as quickly as possible, straight there. If he's doing what I suggested, making this global decision, he would actually be doing something like that. And then this is a great question to ask people, which one did he do? And in fact, moment for pause, that's what he did. So he actually,
wow.
Isn't that something? He actually made this global decision of coming in towards the beach, ran along the beach and back out again. Elvis became Dr. Elvis at that point. He got an honorary doctorate degree from Hope College. There's the provost of Hope College. This is Jim Bolkins. He's the father of Matt Bolkins, of mathematician from Grand Valley. But there he is, hooding Elvis with his honorary doctorate. And I wrote a little addendum to this article, which was published, but I just wrote this article saying, after all, it turns out Elvis does, in fact, make this global decision. So rather remarkable. So that led then to the question of, when should Elvis come in towards shore and when should he swim straight there? So that became yet another paper. Basically, it's a bifurcation problem. Either it's a bifurcation because it's one of two extremes. Either he commits himself, comes into the beach, or else he commits himself and goes straight there. There's no reason to go halfway into the beach. So Roland Mitten from Roanoke College started working on this, and then I started working on it. We joined forces, and so we put this paper together. This is another paper that I've given hundreds of times around the country, and you do the mathematics of this, and it turns out that the bifurcation point depends on basically the question is, when should he swim straight there, and when should he come in towards the beach? And that's the bifurcation point of depending on his swimming and running speed again. When should he swim straight there, and when should he come in? And so that's another nice paper to look up if you want. It's this one got the George Pulley Award from MAA for the best paper of the year for that year, 2008, I think it was. But anyway, without going into all the details of that paper, once I got the results of it, I went back to the beach with Elvis, and given the fact that we started 4 meters in the water, and I threw the ball 4 meters in the water, and using the formula, here's your bifurcation point. If I throw the ball closer than 10 meters away, he should swim straight to it. If I throw it farther than that, he should come into the beach. So let's see what he did. 16, he should come in towards shore, and he did. 9.5, he should not come towards shore, and he made the right decision. Then he blew it. Then he made a couple of good decisions again, then he blew it. And there's your final answers. So the bad news is he didn't do it qualitatively quite right. The good news is he had the right idea. He was consistent. His bifurcation point was somewhere between 14 and 15 rather than 10, but he was consistent in making that a bifurcation point. And if you notice, this was July 2006. It was a hot day in July. It might have been that he was more interested in staying in the water than he was in getting the ball quite so fast. So lots of interesting stuff there. So I say maybe he knows them qualitatively, but not quantitatively. And there's the end.
Well, I really want to thank Tim. I've known about this article, as many of you have, from the College Math Journal from when it was first written. But I didn't know about all of the following stuff up through the bifurcation, nor did I know about the true experimentation that was going on. We have a little time. Are there some questions? Or I'm going to be talking about a similar thing. And so we can share experiences. Have any of you done this sort of least time path modeling in your class? You might put that in the chat as we go. Well, I want to thank Tim very much, and I know how to do that. Okay, and I wish I could get a letter from the Royal Palace, even if it's a rejection, you know. Okay, so I want you to stop.
By the way, I'll just put in a plug that I've got a paper which is, I think, just as useful, if not more so, than this one, coming up at a 4 o'clock talk. So anyone who has a free at 4, come and join me for the barge talk.
Okay.
Very good.